All right. Okay, we'll get started. How's everybody doing? Awesome. Good. Okay, that's great to hear. Your midterms, I posted the grades last night, and everyone's always curious about distributions and whatnot, and so the median was 83.7. First quartile 72.09, and third quartile 93.02. Okay, so I feel pretty good about this distribution. This seems to be in line with performances in past courses, and kind of you know, I always aim to have when I write an exam, I try to aim to have the median somewhere in the 80s, and Q3 in the 90s, and Q1 in the 70s, and that's that. I grade on a straight scale. I don't curve, so because I don't like the idea of students kind of competing against each other to like get a better grade or something like that. So so what you earn is what you earn, and that's going to be reflected in your final grade. I guess I want to just you know, address just a couple things about the exam, and this is this is mostly for students who didn't perform as well as they would have liked. You know, and that happens every time there's a test. Sometimes you know, I know some of you are studying very hard, and you know, doing all of the homework exercises, coming to class every day, doing everything that you're supposed to be doing, and then yet on the exam, on a test or a quiz, maybe your score isn't where you want it to be. And I know it can be frustrating. I know it can be discouraging when that happens. And I can only kind of offer you, you know, the consolation that you know, there's excuse me, got something. That's all I can ask for. I can only ask for you to, you know, try your hardest and do your best. And, you know, grades are an imperfect measure. They always are. Tests and scores, they're always an imperfect measure. They never are truly able to know exactly how well a student has mastered the concepts. I also just want to say, you know, the grades that you get on a test or in a class are never a reflection of who you are as a person. You as a person are so much more than your academic achievements. And I know right now you guys are all at UCLA because, you know, up until this point in your life, probably you were always the top students in your class in high school, and you know, and it feels uncomfortable to be in a situation where you know, maybe some of the exams and the testing and you know, I know it doesn't feel good to be below the first quartile, okay? But that said, again, grades are, your academic performance is never a measure of who you are as a person. You know, you are so much more than just that. And so, you know, I don't want anyone's mental health to suffer, to, you know, experience anxiety or depression or anything of the sort due to stuff in the course here. You guys are always welcome to view and examine your tests, see what you got right and what you got wrong. Just come during office hours, or, you know, basically I'm on campus Monday and Wednesday, you know, until around 5 or 6 o'clock. So anytime after, I teach a class that ends at 3 o'clock. So anytime after 3 o'clock, come to my office and you can take a look at your test. I do keep the tests because I like to reuse questions from quarter to quarter, so so I do keep them, but I'm happy to show them to you and have you guys review them. There's a few things I need to adjust. I might have already said this, but anyway, when I was making the syllabus, I basically just clicked the little calendar in the lower right-hand corner, and anyway, and I set the dates that way. But so I made the mistake of saying there's going to be Lab 5 on September 2nd, which is a holiday. So I'm just going to scratch Lab 5, okay? And I think I said each lab is 2% of your grade. So so I just already put in Lab 5, gave everybody 100% for Lab 5, okay? So you just have 4 lab assignments that you're responsible for, and they'll cover 8%, but then everyone gets a free 2% there. The homework I've also put in the gradebook. Again, everyone just gets full credit for homework. I'm under the assumption that you guys are doing it to study. As far as attendance and class participation, I wanted to get that online poll thing to work. It didn't work, so probably I'm gonna have to give free points there also, okay? So I think you guys are getting something like 17, at the end of the day, 17 percentage points free, factored into your grade book, because of, I guess, a mistake I made when writing the syllabus, and then just technical problems using the online poll system, okay? And then quiz 3, again, I didn't realize, I don't know about, probably not free points. We'll see what happens, okay? I was expecting to have today's lecture and Monday's lecture, and then you would take, you know, the quiz on Wednesday, September 4th, but the quiz, it's still scheduled for September 4th. I'm probably gonna have to rewrite it and stuff, and we'll just see how much I'm able to cover in lecture today, okay? So obviously I can only ask stuff that I've covered, or at least, you know, so anyway, we'll figure that out. So anyway, that's what we've got going on. Lab 4, you guys will cover in discussion section today. Okay, any questions, at least regarding administrative and logistical stuff with the class? Yes?
I forgot, is the final cumulative?
Is the final cumulative? This is the question. The answer is always kind of yes, sort of, but definitely it's going to focus on stuff after the midterm. Much heavier emphasis, probably like 80% stuff after the midterm, maybe about 20% stuff from before. The stuff from before is probably going to be a little bit more conceptual in nature, less calculator heavy for that 20% of stuff that comes before. You know, the 80% that comes after the midterm, definitely lots of calculator involvement there, but that's kind of the balance that I'm aiming for. Anything else? Okay, so we will continue on, and oops, let me just close this. All right, and so let me just kind of point back to this big picture stuff that we talked about on the first day of class, and yeah, a lot of the stuff that we do week to week and in class is, you know, a little bit more detail oriented and a little bit less big picture stuff, but I guess Today I just want to kind of pull it back, look at the big picture again, and before I get into kind of our next section here. Okay? So the big idea is that we can draw conclusions from data, okay? We're going to draw conclusions about populations based on our samples of data. We talked about the kinds of conclusions you can make, whether it's from an observational study or an experiment or anecdotal evidence, things like that. But here we're gonna starting today, and yeah, let's see. So I'm just counting the lectures I have left. So today is 4th week Wednesday, which I have. 5th week Monday is a holiday, so I've got 5th week Wednesday, and then 6th week Monday. Okay, and then the final exam on 6th week Wednesday. So I only have 3 lectures left. Wow. Okay. I'll probably have to rebalance what I wanted to cover. But okay, so a lot of what we're going to be talking about is making those conclusions. How do we make conclusions about the populations? And you know, we already said stuff about making predictions about what happens on average, and we said it's nearly impossible to make predictions about an individual observation. And really, starting today, I guess in our last 3 lectures, we're going to look at basically at points 3 and 5. We've already covered a lot of this probability stuff, okay? But what we're going to see is, you know, in our data, we might see associations between variables in our data, okay? And we've talked about this a little bit already with the question of, are these 2 variables independent or not independent? And right now we said if you take the probability of A and if it's equal to the probability of A given B, if those 2 things are equal, then we say they're independent. So if the probability that someone drives a truck is independent of whether they are, you know, from California or Texas, then that means we have the same proportion of people who drive trucks in Texas as we have people who drive trucks in California. If they are not independent, if there is an association, then we would expect to see those proportions to be different. And probably they're not independent. Probably in Texas, based off of stereotypes, probably more people in Texas drive trucks than in California. I don't know, probably California. I think the stereotypes are more people in California drive hybrids and electric vehicles, and in Texas you got more people driving trucks and I don't know, whatever, I guess trucks. So we might observe an association between variables in our data. And what we're going to explore, I guess today and later on, is that just because these 2 probabilities or proportions are different, you know, the probability of A is different from the probability of A given B, that may or may not mean the association exists in the real world, okay? And the association we see in our data could be caused by the actual existence of the association, or it could be just a result of a random fluke. And so, you know, we learned a lot of probability. We covered a lot of like normal probability and probability rules, and that will play the role of helping us understand which random flukes are likely or unlikely to happen. And then, and we combine our knowledge of probability along with what we observe in the data to make conclusions to see if an association we observed in the data is likely to be a result of a random fluke or not, okay? And so that's what we want to do, okay? So kind of the example is, you know, let's say you go decide to survey some students, okay? And I don't know, you survey some South Campus majors and North Campus majors, and I don't know, you ask what proportion of students wear glasses, and maybe when you survey the South Campus students, maybe you get something like 30 out of 100 people wear glasses. And then when you go North Campus, you get something like 27 out of 100 people wearing glasses, okay? And so if we were talking about, is there an association, based on what you've learned so far, you would say the probability of wearing glasses if you're South Campus is 0.3. The probability of wearing glasses if you're North Campus is 0.27. Okay, 27 out of 100 and 30 versus 100. And right now we would say because 0.27 is different from 0.3, there's an association, or that they are not independent, okay? What I want us to consider is that, you know, maybe I got that difference of 0.27 versus 0.3. Maybe that was just a result of my random selection. If somebody else did the same survey on a different day and they selected different random people from South Campus and different random people from North Campus, maybe they would get 28% and 28% and find that there is no association. Or maybe they would get something different where that in North Campus it's 31% wore glasses and 26% in South Campus wore glasses, or something like that, where now we're seeing the opposite, where more people in North Campus wear glasses versus South Campus. And so we want to explore the possibility that maybe the differences we observed in our data is just from random chance, and not necessarily because there's actually a difference in the proportion of people who wear glasses based on whether they are a North Campus or South Campus major. Okay, does that kind of make sense? What's going on? And so that's what we're going to explore today in chapter 7, and we'll see how far we get there. Okay. All right. So in chapter 7, this is kind of about the big idea we want to talk about here is the sampling distribution. Okay. Something happened again. Okay. And I guess before we start, we got to just start off with some terminology. And we've covered a lot of this before, but we'll just redefine everything once again, just because it's important that we're all on the same page with terminology. So this will be a good refresher here, okay? So we start off talking about the population. The population is everyone who's relevant to the question we are asking. And in general, it is too big to be studied directly. Okay, we don't have the resources to ask every single person in the population. Okay, the population has properties called parameters. Okay, so things like the proportion of the population, or the mean of the population. So I'll say examples: the proportion of the population, or the mean of the population. These are These are parameters, okay? Proportion of the population, we will just call this the population proportion. And we just use the symbol P, okay? The mean of the population is, this is the population mean. And we use the symbol mu. Okay. Because the population is too big to be studied directly, we randomly select, or I will say we study a sample instead. A sample, which is a selection taken from the population. And we often assume the sample was selected randomly. But again, selecting a sample truly randomly is not an easy thing to do. So, so we're going to study a sample instead. Sample, we're going to assume, was selected at random, and kind of the corresponding value in the sample is called a statistic. So you've got the population has parameters, and the sample has statistics. Okay. Okay, and so our examples are the proportion of our sample of the sample, which we will just call the sample proportion. And the symbol we use for that is p hat, or the mean of the sample. Which we'll call the sample mean. Is S. Oh, you know what, let me also include standard deviation. So sorry, squeeze this in above. The standard deviation of the population, or population standard deviation, is sigma, and then we've got the sample standard deviation. I'm sorry, sample mean is, I apologize. Sample standard deviation is S, sample mean is X bar. Okay. Okay. Again, and I think I talked about this on our very first day of class, where we said selecting the sample randomly is actually a very difficult thing to pull off in real life. That you know, you need a sampling frame which lists off everybody, and that's really hard to do. Okay, and so, you know, for the sake of kind of the mathematics, the mathematical principles that we're going to assume, or kind of allows us to do the calculations that we do, you know, we have to assume that the sample is selected randomly. But again, in real life, whenever you read a study, one of the questions you should ask is, how is this sample selected, okay? You know, I don't know if you guys ever watch Family Feud. It's just a stupid game show, but, and I guess there's lots of memes with Steve Harvey and the ridiculous answers that people have. But they always talk about survey says, and it talks about like what were the answers that they give. And I always want to know, who are they surveying, okay? Like, how did they get their survey? Because I highly doubt that this is a truly random sample. There's other games that where, you know, you are giving responses based on random random samples, okay? Or not random samples, but survey data, okay? And it'll say like, you know, this proportion of people said this and that, right? Sometimes you'll go to a different a website. Often things on, sometimes I see people put stuff on Facebook and they'll say like, please answer this poll, okay? They'll create like a Google form, a Google survey form, and then they'll email it out and they say, please respond to this thing. And I'm always just thinking, this survey is not going to produce any kind of reliable data whatsoever, okay? Because whenever there's a survey online, some people enjoy just giving bad information. I think there was like a thing of like, you know, whenever they ask, what should we name? What should we name the boat? What should we name the moon? What should we name this? It's always going to be like Boaty McBoatface and Moon McMoonface or something like that. You know, I think this was like a decade ago, but they asked, you know, where should Justin Bieber go touring internationally? And, you know, it was like North Korea. You know, this is not an accurate reflection of the opinion, because you're not doing a truly random survey, okay? If you, Google actually offers a surveying service. It costs money. It costs like 10 cents per response. And they survey YouTube users, and they're hoping that, and they've got some kind of algorithm to try to get a representative sample of YouTube users. And that's why sometimes instead of playing an ad, you have to answer a survey question. And that's because when you answer that survey question, they're making 10 cents off of whatever click you give them, okay? But again, who knows that people are even being honest in these answers, right? It's like, which of these brands have you heard of? And it's like, I've probably heard of all of them, or maybe none of them. I don't know. You guys get surveys on YouTube, right? Okay, so this is not just something that's happening to me. But yeah, that's part of their, they're making money off of that, right? So do you prefer the surveys versus the ads, or do you, nobody cares, right? You just want to watch the video. So, so anyway, I guess Google has shown that the results of those YouTube surveys are close to being representative, like a truly random sample, and so that's why they can sell each click for 10 cents. But otherwise, if you just want to do a survey and you send out a Google form to your friends, you are not going to get any reliable data, okay? Like, if anything, one thing I want you to learn from this class, don't send out Google Forms and try to use that as a source of survey information, okay? If you've got a club and you want to know how people feel about something, a Google form and you email that out is not going to give you anything reliable, okay? So don't even bother, okay? A lot of money is spent by news organizations just to kind of predict whether a certain like legislative proposal is popular or not, okay? They'll say like, how do people feel about this current issue that's being debated in government? and it requires people to answer phones and people to talk. And I don't know if you've ever gotten a random phone call where somebody called you asking for your survey opinion. Sometimes it happens. I don't know if you actually sat down and answered their questions for 15 minutes. If you said no because you didn't feel like it, you're probably like most other people, and it's hard. It's hard to get survey information. But anyway, I don't even want to dwell on that. Let's talk about sampling distributions. Okay, so this is the idea of the sampling distribution. So we've got our terminology down. Okay. Okay. So a sampling distribution is the distribution of a sample statistic is the distribution of a sample statistic's, I guess, possible values for kind of the range of possible samples. All right, that's a weird sentence. But here's the idea. Okay. The idea is you want to estimate some proportion of the population, right? So in the population, this proportion of people have a certain opinion, okay? In the population, you know, a certain proportion has a trait. Okay, so this is just, I'm being very generic here, okay? In the population, a certain proportion has a trait, right? Okay, so we'll say the population proportion is P. Okay? I don't know. Maybe we'll just say, I don't know, what percentage of the US population do you think has access to a Netflix subscription? I don't know. Are there numbers on Netflix subscribers? How many Netflix subscribers in the US? Oh, look, somebody already asked this. Okay. June 2019, 60 to 90 million members in the US. Okay, so what is that? So let's go somewhere in the middle, 75 million, okay? 75 million out of 300 million, what's that? 25%, okay? All right, so we'll say, so example, is that higher or lower than you expected? Higher? Okay, well, so we'll say example, 0.25 of the USA has Netflix. All right, now, let's say we don't know this, right? Okay, so here I'm cheating because I looked up the answer. But let's say you wanted to do some research and you said, well, I want to just survey people and see what proportion of people have have Netflix. So what you're going to do is, again, the population is too big. And so what you do is you just randomly select people, okay? And so I'm going to just kind of gather these. And we get a random sample here. So maybe you survey, 100 random people. All right. And if you survey 100 random people, how many might have Netflix? Maybe 25, but is it possible that you get like 23 people have Netflix, or 29 people have Netflix, or even 30 people having Netflix? Okay, so what we get is we get 100 random people, and I'm going to just say 28 have Netflix. Okay, so what we have is your p hat is going to be 0.28. Now, what if somebody else goes to the population and takes a different random sample? Okay, so we're going to have another random sample. Okay, and then again, we're going to have 100 people. And then maybe this random person gets 24 subscribers. So p hat is 0.24. Okay, and what if you just keep doing this over and over and over again? So you're going to get a sample, you're going to get a p hat, here's another sample, and another p hat, and so on and so forth, dot, 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 okay? All right, so can we kind of imagine visually what, or just hypothetically what's going on? Okay, and what we're going to do is we're going to keep track of all the different p hat values that we see. Okay, all right, so what kind of values of p hat do you think we'll see? I just want you to kind of think and get some intuition about this before I go on. So what do you think will be a very common value of our sample proportion? Anybody? All right, so, okay. Do you think p hat being 0.24, is that going to be a common value? Will this happen a lot, or will this happen very rarely? It'll happen a lot, okay. What about p hat being 0.25? A lot, okay. P hat 0.30? Maybe. Do you think I could get a sample where p hat is 0.5? Do you think it'll happen a lot? No, okay. So what about a random sample where only 9 out of 100 have Netflix? Will that happen a lot or not often? Probably not that often, right? So the idea is in the proportion, we're assuming, 1/4 of people have Netflix, okay? 25% have Netflix. And so when I take a random sample of people, we expect something around 25% in my random sample to have Netflix. Now, because it's random, sometimes it's going to be higher, sometimes it's going to be lower. But while it is not impossible to get, excuse me, a random sample where 50 people have Netflix, we don't expect that to be a common thing, okay? And again, while it's not impossible for a random sample to have only 9 people having Netflix, we again don't expect it to be very common, okay? And so if we were to draw a distribution Sorry, I don't know what's wrong with my voice. If we were to draw distribution of the p hat values, what would this look like? How would you describe its shape? Where do you think it would be centered? Okay, so this is the sampling distribution, right? So what kind of p hat values will we see? What kind of values of p hat will we see? Okay, so because the population is 0.25, population proportion is 0.25, we expect p hat to be close to 0.25, okay? But we also recognize that p hat can be higher or lower because it's a random sample. Okay, and so the shape that we would get is that p hat being 0.25 is going to be kind of most common, and then we're going to get something that is fairly unimodal and symmetric, okay? And I'm going to just kind of jump ahead to the conclusion without even, and we can simulate this, okay? But we're going to get something that looks like this, okay? And this is basically the result of something called the central limit theorem. This is a kind of this mathematical idea. We're not going to bother proving it, but we're just going to say thanks to the mathematicians who did prove it and use its result, okay? The result of the central limit theorem says basically the distribution of p hat, okay, all the different p hat values, will look very much like the normal distribution. And I just want to, again, pause and make sure that we are okay with this concept of the distribution of p hat. It's the idea of if you take a random sample and calculate a p hat for your sample, and I take a random sample and calculate a p hat for my random sample, and everybody takes different random samples and calculates p hats for their different random samples, and we kind of compile them, what is the distribution of p hat values, okay? And what we're going to find is that it's very similar to the normal distribution. The center will be equal to the population mean. Which is going to be equal to p, and the standard deviation is given by this formula. p times 1 minus p divided by n. And what we notice is that n, the sample size, is in kind of the denominator here, which means larger samples result in smaller standard deviations. Okay. Technically, the distribution of p hat is not exactly normal. The normal distribution is continuous, and the distribution of p hat is technically not continuous. If I'm drawing random samples of 100, I'm either going to have 24 Netflix subscribers, or 25 Netflix subscribers, or 26 Netflix subscribers. I'm not going to have 25.5 or 25.2 or 25.1. Okay. Yeah. Question.
Isn't the population mean mu?
The population mean is mu. What did I write? P. Okay. Yeah. I'm sorry. The center will be equal to the. Sorry, I should say population proportion. I apologize. Thank you. Thank you for catching that. Yeah, so the center is equal to the population proportion, which is, in our case, 0.25, okay? I can kind of show a simulation similar. Okay, so this is not Netflix subscribers, but here we've got this candy machine. And inside this candy machine, we've got yellow and brown and orange pieces of candy. And I'm going to just say 25% in the big machine is orange, and we're going to take a random sample of 100. And if I take a random sample of 100, then we're going to get, it's just kind of mixing everything up, and it's drawing out, it's taking a while, huh? It's drawing out a bunch of pieces, okay? And when we do our random sample, we end up getting 28 orange pieces of candy, okay? So, so what it's going to do is it's going to create a dot plot down here at 0.28, right? Here, I'll just do another random one, okay? And here, 29 are orange, so it puts a dot there. And here's another random, okay, in this case, only 23 were orange. Okay, so we put a dot at 0.23. And I can do this kind of like 10 at a time. And so it's gonna do this 10 times, and it's gonna add 10 dots to our plot, okay? And I can kind of do this, and it's going to add 10 more dots on our plot, and what we see is that, you know, so far around 0.24, 0.25 are most common, okay? And, you know, we got a sample with around 35% orange and a sample that looks maybe like 14% orange. Let me go ahead and just do like 100 of these things. Okay, and we're starting to see something that looks closer to the normal distribution, okay? The dots are so close that they've basically merged into lines. Let me go ahead and just do like, maybe I'll do 1,000, Okay. Okay, and so this looks a lot like the normal distribution. I can overlay the continuous normal distribution, and we can see that here I've done 5,663 of these random samples, okay? And when I take random samples, you know, I'm getting 24, 25, 26% for my sample proportion quite often. I do get 30 and 31%, but those happen with less frequency than getting 26%. And I do get sample proportions of around 40% or as low as 10%, but it's with much lower frequency, okay? And even though I've done 5,600 of these samples, not once did I get a random sample where 50% were orange or something less than 8% are orange, okay? So it's not impossible, but it just didn't happen even after, you know, over 5,000 attempts, okay? And it looks like after 5,000 attempts, you know, it looks like I got 40% orange maybe only a couple of times, okay? And so this gives us, this is the distribution that we observed by actually doing the simulations, and we can see that we can approximate this using the normal distribution, okay? And so now that we've got the normal distribution, to approximate it, we can start asking questions about what kind of samples are possible. So I could ask a question and say, you know, if 25% of the population subscribes to Netflix, or if 25% of the candies in the bucket are orange, I could ask, what is the probability that a random sample of 100 people ends up being 30% subscribers, or 30% orange, or something, okay? So, so let's try this. Okay, so what we've got, the summary of the previous slide is that p hat comes from a normal distribution where the mean is p and the standard deviation is p times 1 minus p over n, okay? And so we're going to say, so we'll do kind of the candy example, and we'll say this time in the bucket 0.3 of the candies are orange. And I will take a random sample with we'll say 60 random pieces. And I want to know, what is the probability I get 35% orange or more. 35% or more is orange. Does that question make sense? Okay. No? Maybe. So again, here in the population, this is our bucket, but in the bucket, I guess we've counted all the candies and we know exactly 30% in the bucket are orange. And if I take a scoop of 60 random pieces, okay, so we're going to take out, a scoop. Okay, and this has 60 pieces. Okay, so we're going to take a scoop of 60 pieces and I dump those out. I might get 30% orange in my scoop. Maybe I get more. Maybe I get less. All right, and I want to know what's the probability that my scoop ends up being 35% orange or more. Okay, so so how would we go about doing this? Okay, so what we want to know is what is the probability that p hat is greater than or equal to 0.35. Okay, and right now, what is the distribution of p hat? The distribution of p hat is normal. What is the mean? Is the mean 0.35, 0.3, 60? What is it? It's 0.3, okay? It's the proportion in the bucket, okay? So this is the population proportion. Okay, and what is the standard deviation? Okay, the standard deviation is going to be p, 0.3, times 1 minus p, which is going to be 0.7, divided by n, which is my sample size of 60. Okay, and so this we get normal distribution centered at 0.3, and what does this multiply out to? So I'm going to do square root of 0.3 times 0.7 divided by 60. Okay, and I get 0.05916. Okay. All right, and so so here I want to know what p hat, what's the probability that p hat is greater than 0.35? Okay, so I'm going to put 0.3 in the middle. I'm going to draw a line at 0.35, and I want to know what is the area to the right. Okay, so what is the next thing I've got to do? All right, so in order to answer this question, I would change all of these into z-scores. Okay, so we're going to go from probability that p hat is greater than or equal to 0.35, we're going to change to z-scores. So this becomes probability that z is greater than or equal to something else. Okay, so z, what is my z-score for this? I'm going to put in 0.35. I subtract off the mean. What is the mean? 0.3, and I divide by my standard deviation, 0.05916. Okay, so for this, I'm going to do 0.35 minus 0.3 divided by my previous answer, and I get 0.845, so just round off to 0.85. So now I want to know, what is the probability that z is greater than 0.85? So now we look this up in the table. Okay, and what's my answer? So the area to the right of positive 0.85 is going to be the same as the area to the left of negative 0.85. So I'm getting 0.1977. Is that right? Does that feel okay? All right, let me give you guys, another example to work through. Okay. All right, so we will say, let's say that in the population, I don't know what, let's ask Google, what proportion of households have a dog? Okay. 68% of US households own a pet. Okay. I want to know dogs though. All right. 60.2%? No, 60.2 million. So what's that? How many households are there in the US? I have no idea. Okay, let's just go with pets. Okay. 68%. Okay, wait, 85 million is 68%. So if 85 million is 68%, then 60.2. All right, so. All right, I'm spending too much time. Okay, 68%, so 85 divided by 0.68 is 125. Okay, so 60.2 divided by 125 is 48. Okay, so we'll go with 48% have dogs. Okay, I'm just making this up, right? Kind of based off of this. All right, so let's say that in the population, 48% of households have a dog. Okay, so 48% of households have a dog. You're going to randomly survey, let's say, 100 households, okay? Okay, and I'm going to just say, what is the probability that over half of your survey have a dog? Okay. So in the population, less than half, only 48% have a dog. But we want to know what's the probability that you end up getting a survey where over half of them have dogs. Okay, do you guys want to try this out? All right, so I'll give you a few minutes. It's very similar to the previous example I did. So just adjust your numbers accordingly. And we'll go from there. I'll give you guys a few minutes to work on this, okay? Let's start going over the answer here. All right, so it says in the population, we're going to assume that 48% of households have a dog. We're going to randomly survey 100 of these households. And what is the probability that over half of your survey have a dog? Okay, so what we want to know, what is the probability that our survey's proportion, our p hat, ends up over 0.5, okay? So we want to know what's the probability that over half of our survey has a dog, okay? And so to use this, via the central limit theorem, we have p hat comes from a normal distribution where the mean is p and the standard deviation is p times 1 minus p over n, okay? And so this becomes p hat, normal distribution, where the mean is the proportion of the population, 0.48, and my standard deviation is 0.48 times 1 minus 0.48 divided by my sample size of 100, okay? So I'm going to go ahead and punch this into my calculator, which, let's go ahead, we got square root of 0.48 times 1 minus 0.48, which is 0.52. We're going to divide that by 100. And I get pretty much 0.05, 0.0499999599, okay? P hat is n.48, and this is 0.04, what is it, 0.4996, okay. So pretty much 0.05, okay? And we want this. So, you know, our picture, if we draw a picture, we're centered at 0.48, and we're just a touch higher at 0.5, and we want to know what is the probability that we're greater than 0.5. Okay, so we convert this to z's. We're going to do probability that z is greater than something. Okay, so my z is 0.5. I subtract off the mean of 0.48 and divide by 0.04996. Okay, we'll go ahead and try this. So I've got 0.5 minus 0.48, and I'm going to just divide by the previous answer that I got, and I get 0.40. Z is equal to 0.40. Okay, so that's what I want to know. What's the probability that z is greater than 0.4? So now we look this up in the table. Okay, and I can do, I can look up 0.4 and do 1 minus that. So 1 minus 0.6554, or I can just look up negative 0.4 and I get the same thing. What is it? 1 minus 0.6554. Which is going to be 0.3446. Okay. So, you know, what this says is that even though technically less than half of households have a dog, you know, it's just a little bit lower, okay? When you do a random survey, you've got about a 1 in 3, a little over 1 in 3 chance, 1/3 chance that you might come to the conclusion that more than half of households have a dog, okay? I mean, I don't know what the consequences of such a conclusion would be, but it's possible, right? And you know, stuff like this, maybe if we're not talking about dogs, but something, you know, politically, if we've got surveys, you know, it might be true that in the population, less than half of the people support some kind of proposed legislation, okay? But then when you do a survey, you might come to the incorrect conclusion that more than half, a half or more, support the legislation, okay? Whatever it is that, that might be proposed. And there's no way to know, okay? When you survey the 100 households, if you don't know what the population looks like, you don't know if your number is too big or too small, okay? So when you survey 100 random households and you get something like 52% of them have a dog, you don't know if that 52% is higher or lower compared to the national kind of proportion, national average. So, so that's what we've got going on, okay? And so the sampling distribution gives us an idea of, you know, what kind of variation we see in p-hat, okay? Whether our samples can end up with p-hats that are too big or too small. All of these things are possible, okay? All right, there's a couple of conditions. So we kind of went through all of this math, but there's technically, okay, this is where we have to just say conditions to use the central limit theorem. So this is your So the central limit theorem is the idea that we can use the normal distribution to answer questions about p-hat, okay? Central limit theorem allows us to use the normal distribution answer questions about p-hat, okay? Because if the reality is that p-hat does not follow a normal distribution, right? So the real distribution of p-hat are all of these bars, okay? It's not technically continuous. The normal distribution is continuous, and it's technically all of these bars. But the central limit theorem says, you know what? These bars and the normal distribution are similar enough that let's make our lives easier and just use the normal distribution, okay? I don't want to calculate all of these bars. Technically, the bars follow the binomial distribution that we talked about. And so that, you know, that's the technical thing. And so, you know, if you want to be pedantic, you can say actually it follows the binomial distribution and blah, 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 blah. The central limit theorem says, you know what? It's close enough to the normal distribution. Let's just use the normal distribution, okay? So that's what it says, okay? To answer questions about p-hat, but, you know, in reality, p-hat follows a binomial distribution. But there's some, the central limit theorem doesn't always work, okay? You cannot always approximate the distribution of p-hat with the normal distribution. And so here, these look pretty similar. But, you know, if we had something different, okay? Let me just do an example here, okay? So if you only take samples of, like, say, size 10, okay, you're gonna get something like 20% orange, maybe 30% orange, maybe 0% orange, 10% orange, things like that. So you'll never get, you know, 25% or something like that. Let me go ahead and just do a bunch of these samples here, okay? Okay. This, if your sample size is only size 10, this is what your distribution looks like, okay? And I would say this does not look like the normal distribution, right? So here's the normal distribution, and it doesn't quite work, okay? The normal distribution goes below 0, all right, in this case, which is never going to happen, okay? If we just look at this, it feels uncomfortable saying this is a lot like the normal distribution, okay? And that's because we know we can only get either one orange piece of candy or 2 or 3, and therefore my proportions that we get are only going to be like 10%, 20%, 30%, or 40%, something like that. Stuff like that, okay? If I do samples of size 15 or something like that, and let's say only 10%, okay? Again, when I draw samples, this doesn't quite look like the normal distribution. And so when your samples are small, using the normal distribution as an approximation is not a good idea, okay? If you have much bigger samples, okay, samples of size 25, even then it seems kind of small. Maybe samples of size 50. Okay, as we increase our sample size, I maybe regret pushing this button. Okay, so here, with a big enough sample, we get something that this feels a little bit more normalish, okay? And so basically, the condition that we need to fulfill is that our sample size needs to be big enough, okay? So if your sample size is too small, it's a bad idea to approximate the distribution using a normal distribution, okay? So condition to use the central limit theorem. Central limit theorem allows us to use a normal distribution, but if your sample size is small, it is a bad idea to use the normal distribution as an approximation. Okay, and so kind of your rule of thumb, okay, so the recommendation is that n must be large enough to have at least 10 yeses and 10 no's. So if we're talking about the orange pieces of candy, you need to have at least 10 pieces that are orange and 10 that are not orange, okay? Or you need to have at least 10 households that have dogs and 10 households that don't have dogs, okay? Whatever it is that we're talking about, you need at least 10 yeses and 10 no's. Or, another way to put it, or in other words, n times p has to be greater than or equal to 10, and n times 1 minus p also has to be greater than or equal to 10. Okay, so that's your sample size needs to be big enough, okay? So this is known as your large sample condition. Okay. All right. The other big things, okay, is other conditions. Is basically samples are selected at random. Samples are selected randomly and independently. Okay, and we kind of said this at the very beginning, and this is just something you need to check beforehand for any kind of analysis, is just you have to ask, is this sample reliable, right? Is this sample random and independent? And again, if your sample comes from a Google form that somebody emailed out to their friends, there's no use applying any of these statistical methods because your data is going to be junk, okay? If you've got junk data, you're going to draw junk conclusions, okay? If you put a survey up on Twitter, okay, you can't draw any kind of conclusion from that. I don't even know why they have a survey feature on Twitter. It just leads people to make bad conclusions about anything, right? So Facebook and Twitter, they have these survey poll features, you know, poll your friends or poll whatever. I don't think there's anything reliable that can be drawn from something. Okay, I'm sure if we looked up ridiculous Twitter polls, let's see, funny polls. Oh, I'm scared of what we're gonna get. Okay. Most plausible. Ghosts, vampires, aliens, time travelers. Okay, I don't even know what this is supposed to be talking about, but sure. Okay, so, you know, ridiculous polls. Anyway, don't even bother if you have bad data, okay? Bad data sources. Okay, and then the last one is kind of related to this selected randomly and independently, is if the sample is selected without replacement, the population needs to be at least 10 times bigger than the sample. This we might call the big population condition. Okay. And the reason for that is when you sample without replacement, what ends up in your sample actually changes what remains in the population. So just imagine a deck of cards. A deck of cards has 52 cards in it. 26 of them are red and 26 are black. Okay, the first card you select, let's say it's red, okay? After you select that, then what remains in the deck are 25 red and 26 black, okay? So while your first card had a 50-50% chance, 50-50 chance of being red, what remains, the second card is technically not 50% red. It's 25 red, 26 black, okay? And so you can imagine if you've selected a sample of 10 cards from the deck, and 8 of them are red and 2 are black, then, I don't know, you got something different remaining in the deck, right? So you got 26 minus 8 is 18. 18 are red and 24 black, okay, of what remains in the deck. And basically the idea is, well, if you selected less than 10% of the deck, so, you know, you take one card and it's no longer half red, half black, it's 25 red and 26 black. We say, well, you know, that change, we can kind of ignore it, okay, it's negligible. But once you start taking more than 10% out of the population, what remains could actually be impacted by what's in your sample. And so, so drawing without replacement would technically violate the condition that things have to be random and independent, okay? Because when we're saying random and independent, we're basically saying every single card I select has an equal chance of being red or black or things like that. And if you're selecting without replacement, that's no longer true. Most surveys and samples are done without replacement, but usually it's okay because the population is much bigger compared to the sample size. But again, if you're dealing with a small population, let's say your population is like an elementary school where there's, I don't know, 600 students total or something like that, okay? When you take a random sample, you have to be careful about either, if you're going to take a random sample without replacement, you don't want to survey over 10%, okay? Or you take a random sample with replacement, which might mean you survey the same student twice and they get included in your sample, but that's actually going to be better, okay? Surveying with replacement if you want to get a representative sample. All right, is that all right? So these are the conditions that we kind of have to make sure are true, and probably the most common issue is getting the large sample. It's costly to get a large sample sometimes. So if you're trying to track down, you know, something very rare, it might be tough to get 10 yeses, okay? You might want to know, you know, what percentage of people have this very rare condition, okay? Maybe like what percentage of people have 6 fingers on their hand, okay? It's not 0, okay, but it's not a very high number, and you might have to survey a lot of people before you get 10 yeses, okay? And so in that case, it might not be possible to use the central limit theorem, and you're going to have to use some kind of different, probably the binomial distribution to answer your questions, okay? All right, let's look at our first application of this, okay? So we've talked about sampling distributions, all right? And so the sampling distribution tells us what kind of p-hat values are likely or unlikely. And so here's the first application of inference, okay? And this is important. This is our ability to kind of reason backwards about the population, okay? Because earlier we said, let's assume the population has this property. We're going to assume the population is 48% dog owners. We're going to assume the population is 25% Netflix subscribers, or the population is 30% orange pieces of candy, okay? That's great and all for setting up a problem in class, but in reality, we don't know what the population looks like. We don't know the proportion that exists in the population, and the whole reason why we want to do statistics is so that we can draw conclusions about the population, okay? Like we want to know what proportion of the population, I don't know, thinks climate change is a hoax or something like that, okay? We don't know, right? Maybe we want to survey people to figure this answer out. And so what we have to do is, we want to go from our surveys data to make a conclusion about the population, right? So we want to be able to reason about the population based on a sample, okay? So earlier in today's class, we said the population looks like this. Let's talk about probabilities for our sample. This time, we want to go the other way, okay? We're going to say our sample has a proportion p hat, okay? So, you know, okay? And then we want to know, what does this say about the population. Okay? I don't know. I'm curious. I have no idea. What proportion of the US are climate change deniers? US is hotbed of climate change denial. Okay, sure. Okay. That looks like 13%. I don't know. Total of 13%. Okay. All right, so our sample has a proportion p hat. What does this say about the population? Okay, so we'll say this is based on a survey, right? So it doesn't, this is some survey project. So we don't actually know, but we're gonna just say, okay, so we'll say a random sample found that, and I'm gonna just make up some numbers, blah, blah. Let's say 26 out of 200 people, 200 randomly surveyed people did not believe climate change was caused by human activity. Okay, I think that's what that website said. Okay. All right, so we're going to say 26 out of 200 randomly surveyed people did not believe climate change was caused by human activity. All right, so this is just the result of our 200 randomly selected individuals, okay? Now, does this mean that somehow if we were able to survey everyone in the United States, the entire population, okay, would the entire population have the same proportion, right? So what we have is p hat is 26 out of 200. We have 0.13, okay? What does this say about p? The population proportion. Okay. Is there anything we can say? Does this mean that that if I surveyed the entire country, we would get 13% people didn't believe climate change was caused by human activity? Would we get that same number? Or is the population proportion higher than 13%? Is it 13.5%? Or is it lower? 12%? 11%? Okay. The answer is we don't know, right? We don't know what the population looks like. Okay. So here's our picture. The population has some proportion p that we don't know. Okay. We've selected a random sample. And our sample has p hat equal to 0.13. Okay, so what does this say? Based on this, what can we say about p? Is there anything we can say about p? Could p be 15%? Okay, could p be 15% in the population and we happen to get a sample where p hat was 13%? Is that possible? Could p be 10% in the population and we happen to get a random sample where p hat was 13%? Is that possible? Could P be 20%? And we happen to get a random sample where P hat was 13%. Is that possible? Could P be 30%? And we got a random sample where P hat is 13%. Where do we draw the line to say, I don't think the population is this value? What do we do? How can we be reasonable about this? Well, what do we know about P hat? What is the distribution of P hat? So earlier today we said P hat follows the normal distribution. P hat follows, according to the central limit theorem, P hat follows the normal distribution where the center is P, the population proportion, okay? And what the normal distribution tells us is that when we take a random sample, most of the time it ends up near P, okay? The normal distribution says wherever your center is, your random values most of the time end up close to the center. Sometimes it's higher, sometimes it's lower. And so because of that, when we observe a value like P hat is 0.13, we can be confident that the P is somewhat close by, okay? And from the normal distribution, we know that, 95% of the time, a random value is within how many standard deviations of the mean? 2, okay? So the normal distribution tells us that 95% of the time, a random value is within 2 standard deviations of the mean, okay? So we can kind of reverse this and say I can be confident that this number 0.13 is within 2 standard deviations of P. I don't know what P is. But I can be confident that 95% of the time, okay, that this number 0.13, it's within 2 standard deviations of P, okay? All right, so we know P hat follows the normal distribution. Okay, and this is based on the central limit theorem, okay? Assuming these conditions are met, okay, based on central limit theorem. And that says, so the normal distribution says 95% of the time, a random value is within 2, and I'm going to write technically it's 1.96 if we want to be a little bit more exact, okay, is within 2 standard deviations of the mean. Okay, so when I observe P hat is equal to 0.13, okay, I can be 95% confident that P is within 2 standard deviations of 0.13. Okay, I don't know exactly what P is. Maybe it's bigger, maybe it's smaller, but I can be pretty confident that it's within 2 standard deviations of 0.13, okay? Because we know that my random value of 0.13, 95% of the time is going to be, or whenever I draw a random value from the normal distribution, that 95% of the time it's within 2 standard deviations, technically 1.96 standard deviations of the mean, okay? So I can create a range or an interval make an interval for kind of plausible values of p, and it will go from basically 0.13 minus 2 standard deviations. I'm going to actually use 1.96 standard deviations to 0.13 plus 1.96 standard deviations. Okay, so here's the question. What is my standard, what's the size of my standard deviation? Okay, so earlier from the central limit theorem, we saw that the standard deviation is the square root of p times 1 minus p over n, okay? But the trouble is that we don't know p. We don't know what the population proportion p is. So I'm going to just guess, all right? And my best guess, what is my best guess for what p is? There's going to be 0.13, okay? I'm going to just use my sample as an estimate for what p is, okay? Problem is that p is unknown. Okay. So we use p hat as our best guess for p. Okay, so our standard deviation is going to be the square root of p hat times 1 minus p hat over n. Okay, oh, and I'm going 1 minute over. Just let me just summarize all of this on the next slide, okay? So our a 95% confidence interval will be p hat minus 1.96 times the square root of p hat times 1 minus p hat over n to p hat plus 1.96 times the square root of p hat times 1 minus p hat over the square root of n. Okay, this can be combined into p hat plus or minus 1.96 times 1.9 p hat times 1 minus p hat over n. Okay, and so now it's a matter of plugging in our values plus or minus 1.96 times the square root, 0.13 times 0.87 over, I think, 200, and I don't know what that number is. Okay, so I get 0.13 plus or minus 0.046047, which will lead to 0.177 and 0.13 minus that is 0.0833. 0.0833. Okay. Okay, we'll end here. All right, and I'll put up some practice problems so you can prepare for next week's quiz as well. Okay, have a good weekend. Enjoy the extra day off, and we'll see you guys on Wednesday.